right, so, so the last time we were talking a little bit, I told you a little bit about radical extensions, and what they are. They're sort of sequentially, you get extensions by having, adjoining an nth root of an element of the previous extension. These, go along with solvable groups. In a sense, I'm not gonna go through the proof here, but basically a tower of radical extensions, you can use that to leverage that into a solvable group. Notice that if the degree of x is n, then their splitting field f x over the space field k of degree, or I'm sorry, less than or equal to 4. Right, so that was kind of one word. And the Galois group of f over k is a Sn. Here we're assuming that f is split for separable, irreducible f of x. So I'm going to assume that f is separable irreducible. Now, let me point out that these transitive subgroups can be Sn or An, right? Notice S2, S3, S4 are all solvable. If you remember from back in the days in 8510, and it's easy to show this. Sn is not solved for n greater than 5, right? And so what that means is there is a quadratic formula, there is a cubic formula, there is a quartic formula if you have the patience of Job. However, there is no nth degree formula. Can't be done. By formula, so it's very natural to ask what I mean by formula. I mean something that you can write the roots in terms of the field operations and extracting nth roots, right? Any nth roots you want. So if you throw in the standard field operations, addition, multiplication, division, subtraction, and you also throw in this new operation called I'm allowed to take the nth root of anything that I want to field, you still can't get a formula here. Now, so, and let me stress that this is in general, right? So for example, if you have this, you can solve for radicals, as a matter of fact. One obvious root is the fifth root of 2, and there you can extract the fifth root. And it turns out that all 5 roots can be expressed in terms of radicals. Right. On the other hand, not solvable over Q. Right. You can't get formulas for roots of this in terms of nth roots and field operations here. But this is solvable if the base field is R. Okay. Because the extension from R to the complex numbers is a degree 2 extension. So the Galois group is S2. So over the real numbers, this is solvable. Over the complex number, or I'm sorry, over the rationals, it's not. But again, we're just talking about this is kind of just sort of the art of math, if you will. Okay, any questions? I am a huge fan of this kind of stuff. And so we're going to talk a little bit about arithmetic rings, which I think is a natural sort of step if you're interested in things like polynomial equations and field extensions and so forth. Rings that in sort of, to me, I think it's sort of natural extension of kind of polynomial ideals to not necessarily fields, things that are just rings, like the integers, for example. I like this because this is sort of boundary of algebraic number theory and being valid. So we're going to first talk about integral elements and integral closures. Elements. So how many of you have ever heard of the notion of integrality before? So maybe, so let me kind of, I think it's sort of the natural thing. Yeah, there's something about this that's a little bit strange at first, I think. Here, I am going to, I can extend this definition a little bit, but I'm just going to do it for domains here. So instead of fields, we've sort of got the next best thing. These are just commutative rings of identity, no zero divisors. Although again, you can talk about integrality in a more general setting. We say some element of T and T is integral over R. If T is a root of a monic polynomial in Rx. So in other words, so T is a root of this, so there's some kind of relation here. So R monic is important, it turns out. So we say an element is integral if it is the root of something. So let me give you some examples. Well, this is the analog of algebraic in the following sense. Let's say that if R is a field, then T is integral over R. And only if T is algebraic. Right, so it's the analog here. So think about it here. If T is integral and R is field, then this is certainly algebraic because there's your polynomial, right? On the other hand, if T is algebraic, the difference is this might have some coefficient here, A, it's not zero. But if R is a field, you can just multiply that by A inverse and you're good to go, right? So this is the sort of the natural analog of algebraic in this sense. Now, it's still, maybe it's not so clear why we pick monic, but let's look at other examples. If every element of P is integral over Z. So when I say something's integral, I gotta be specific about what ring it's over. Let me make clear what this is. This is all integer combinations of 1 square root of -5. And this is going to almost look like what we were doing in Galois theory thing. I mean, notice that if you look, there's your equation of integrality, because since a and b are integers, then 2a and a squared plus 5b squared are integers as well. So there's your equation of integrality. Notice, however, that this is a little bit different. Notice that 1/2, notice, of course, the quotient field of this is q adjoined with the square root of -1/2 or -5, right? Notice the quotient field of this contains the rational numbers, right? But even the rational number 1/2 is not integral over Z. Notice that this is a root, very small polynomial over Z, namely 2x minus 1. But no matter how much you twist and turn, you can't make this the root of a monic polynomial. Maybe that's not so clear, right? Because maybe in the depths of some Stephen King novel, there's a monic polynomial so big and ugly that somehow 1/2 works out.
Every polynomial that has one half as a root, is a multiple of 2x plus 1 version.
Right, right. But you actually do need some. So let's assume 1/2 is a root of x to the n plus, let's say, m to the n minus 1, m sub n minus 1. Where these mi's are all integers, right? And I think that we're going to see right here that monic is very, very important. So let's suppose that this happens. So I get that, right? Now, I don't know about you all, but my pea-sized little brain hates fractions. So I'm going to multiply both sides of this by 2 to the n. Even, So 1/2 is not. Even though, as pointed out, that it is a root of, 1/2 is a root of a degree 1 polynomial, but it's not monic. We're gonna see how the monic comes into play here in a moment. Let me give you a more exotic example of integral elements, which is kind of fun. Here, I am going to let R this is one of my favorite rings, actually. And in fact, you know what, I'm gonna make this easier, I'm gonna make this. Although I could do, but I will do it before. This is the set. So think of it this way. This is sort of like a polynomial ring that's a little bit kind of, it's injured, right? Because it's missing the x term, right? But you've got x squared, you've got x cubed. So since you've got x squared, now you've got x4, you've got x5, and you've got every power beyond 1. So this is basically all polynomials that has a 0 coefficient for the linear term. So it's missing the linear term. And let's let T be the full polynomial. Yes.
One question, if we have a root, I mean, if we have an element that such that the minimum polynomial of that element is not monic, we can already say that it's not integral.
It depends on what kind of ring you're over, thing.
Okay.
Yeah, so let me, that's a good question. So the question is if you have some element in a domain, say, and its minimal polynomial, is not monic, does that necessarily mean, I don't think that's generally the case if the ring's not infinitely closed, but we'll get to that. So, this ring here, notice that fact, there is sort of no minimal polynomial in this regard, right? Because I'm going to give you a couple of minimal polynomials. This x is a root. I think we could all agree with that. And notice this is my polynomial. Here my polynomial variable is t. This is a monic polynomial, and the constant term comes out of the bottom right. Or that works as well. Right? So notice that x is not an element of here. It's an element of here. But this element is integral over this because it is a root of a monic polynomial whose coefficients come from here. And I gave you two of them, right? Yeah, I've got a quadratic one and a cubic. Notice that this isn't really a minimal polynomial in the sense that this one doesn't divide this one, right? So that's kind of an interesting example, I think. So what do we know about integral elements in the case where the base rings are field? These are algebraic elements. And one of the big theorems that we've proved about algebraic elements is the sum and product of algebraic elements are algebraic, right? So in other words, We had this big theorem that if you had F inside K, usually it's the other way, but so suppose you had K as an extension field of F, and if you looked at every element of K that is algebraic over F, it's actually some of a subfield of K, and it was the algebraic closure of F and K, right? It turns out that we get a similar kind of thing for integrality. It's going to turn out that sums and products of integral elements are integral, just like algebraic. Even though that's, again, it's not clear, right? Just because I've got something that's a root of a monic polynomial, and this is even worse than the fields, right? Because this only applies to monic polynomials. So, let's look at the following lemma. Let's let R be a domain. Well, again, this theorem has a more general, slightly more general analog, but we won't worry about it here. The following conditions are equivalent for some element U and T. Number one, U is integral over R. And number two, there is a finitely generated R submodule A and T such that UA is contained in A. So this is kind of a groovy thing here. This is the analog, and of course, this captures what we did already with regard to the notion of algebraic integral over R. Okay, so that means it's the root of some monic polynomial over R. There is a finitely generated submodule of T such that QA is contained in A. That's all you need, right? This takes this polynomial equation and reduces this. Why is this true? It's rather interesting. It's true. And once again, just like back in the fields, this is going to render some stuff kind of easier. This direction is the easy one. Okay, so let's suppose U is integral over R. Then there exists R1, Ri, and R, such that N was Rn minus 1, N minus 1, R1U. Now, anybody know how I can pick my A? Right, so the burden upon me now is to find a finitely generated R submodule of T such that UA is contained in A. By what now? Yeah, well, this is a module, right? So I wanna be a little bit, so let's let A module of 1 U squared up to U N minus 1.
Right, because it'll have multiplication.
Right. Notice that I think we can all agree that all the powers of U are in T, so this is an R submodule of T if I just generate this over R, right? And notice but this is u n minus one and un, which is minus rn minus one and minus one. And notice this is super redundant because this is already covered here and so forth. And the R zero is covered by one, so this is contained in one u squared. If you have these n elements, you've certainly got every one of these generators here, which is equal to. So there, that takes care of it. So if it's integral, then if you sagaciously pick A to be generated by this, then you're good to go. The interesting part is the fact that just this business right here gives you this relation of integrality, right? So for the other direction, let's suppose, let's see, 2 implies 1. Suppose A, let's say it's generated by A0 or A1 of A. Yes.
There's another result here. If the inverse of u is also, how do you call it? Integral, yeah, then UA is also is equal to A.
Yeah, actually, we're going to see some stuff about the inverse. Yeah, good. Let's suppose that A is generated by these animals right here, so it's finally generated. So we get the following system of equations here. So let me kind of go through it. So we have, for example, let's look at U times AI. Now, what do we know? UA is contained in A, so when I hit one of these generators here, AI by U, it's got to be a linear combination of these generators, right? So I'm going to call this lambda ij aj.
I have a quick question. Why are we using curly braces for A instead of like a generator bracket?
You're right, I should use that here. I meant to write generating set, but generating set is correct. So that's better. I think that was J one again. Find the I. Okay, good. So everybody agree with me on that? So every AI that I hit, there's some lambda ij times aj. It has to be a linear combination here. Well, these lambdas are, of course, right. Anybody recognize this system of equations here? Let me rewrite this in a more, I don't know, convenient form. See if I type it right. Oops.
To avoid like I equals J, right? Like that will just be 0.
What's that?
We can't have
No, okay, it can be. So this is some U times AI. it might require something on the A. This is not necessarily zero on the A.
Okay.
And even if it was, it should reveal itself to us. Right, let me see if I got this right.
Yeah.
Oh, yes, I can't believe it. I actually wrote this down. And this is equal to. Think about you.
Están ahí en varios, o sea, ruido pero bueno.
So. You is a root of this polynomial. Fine. Quotes around this because actually the leading term is not one, it's -1 if n is odd, but that's fixable, right? So. U is integral. Because the polynomial is monic and all these coefficients, lambda i's, they're in R, right? And linear combinations of them and products are not. So now we have that if you have that condition, then you have an equation for integrality. Yes,
Why don't we assume that not all AIs are zero?
what's it?
The statement of the dilemma, why have we not assumed that A should not be zero?
Oh, you mean capital A? Yeah. Let me check my notes, because I definitely should make that assumption, because you could always have A to be the zero module, and that will be true. Thank you. Yeah, so that's an important safety tip there. The module A, I did not say this sloppy up. This is nonsense. Because otherwise you can always trivially do, right? Okay. So here we're gonna rack up our first big payoff for this theorem. Let's let R inside T be domains. And suppose U, V, and T are integral over R. Then so are sums and products and differences. Proof. Yeah, and again, this is just like when we were in fields. I mean, good luck finding the appropriate polynomial. It's just a huge mess. Let A be our zero finitely generated. submodules T. Such that UA is A and BB can B. Notice that module AB, in general, you were thinking earlier, you noticed that, you can't necessarily multiply things from a module together, but we're good here because actually A and B are subsets of T, which is a ring. And so the module AB, if A is generated by some AIs and B is generated by some BIs, and AB is generated by the AI BIs, all possible. And of course, if this is if this is generated by N things and this is generated by M things, and this thing is generated by NM or less things. So now we note that, notice that A plus, or U plus B here, right? Because stuff from the A is absorbed the U and the stuff from the B is absorbed the B, right? And so you're still in AB. And again, we get exactly what we want here. So this characterization for something that's potentially very hard and something that's not too bad at all. All right. If R and T are domains, then this is the set of stuff in T such that T is equal to R. This is the analog, the algebraic closure of a field in a bigger field. This is the set of elements that are integral, the set of elements of T integral. R is a domain and called, so I'm going to throw a definition on my corollary, the integral closure of R. Okay, so let me give you a quick sketch of this. Notice that if R is an all, then R is integral of R. Because R is the root of that very small monopolynomial. So as a set of elements, R is contained in here, no problemo. And of course, by definition, it's contained in T, right? And so the only thing that we have left to show is that the integral closure of R and T is in fact a ring, but here, A, B, here. So is A minus B. Ooh, we did prove A plus B. by A minus B. That follows directly from this too, but let me take this apart, more readily. That has to be in there. B is integral and -1 is integral because -1's in R. So -1 times B is integral, so A plus this integral element, which is A minus B, is here. And A B. So it's right. Okay, so let me give you, some terminology. Any questions? So here's a little bit of terminology. Domains. Of R and T. If RT equals R, then we say R is, integrally closed in T. So if RT equals R, that is, there's nothing new that's integral other than the elements itself. We say that R is integrally closed in T. If RT equals R and T is quotient field, so now we have the special case where T is actually the quotient field of R. Then R is integrally closed. So here's like kind of a terminology warning, right? This is a little bit different than what we're used to for algebraically closed. Algebraically closed meant that there's no proper algebraic extension, right? Every polynomial has all its roots in there. Integrally closed means that there's nothing new integral in the quotient field, right? So the algebraic closure, right, so if you take a field and take its algebraic closure, it's contained in some, it's this big Zorn's level construction. When you take the integral closure, then the integral closure, the quotient field then R so when we talk about the integral closure of R, it's just everything that's integral in the quotient field. So you're stuck there. You don't ever leave the quotient field. If R bar, the integral closure, is equal to R, then we say R is integrally closed. Okay, so that's kind of, so when you see R bar, unfortunately, that means the integral closure. The left out subscript, it's always assumed with the left out subscript that you're working inside its own quotient field. So I'm gonna do this. I'm gonna By the way, anybody give me an example of a ring that's integrally closed? That is, it's integral closure, you don't get anything new. Smart, is it gonna be a smart aleck answer?
I don't know, like, I think if R is Z2, then RT is always, a field. The integral closure is always a field, I don't,
If R is what? now?
yeah, if R is Z2,
Z mod two?
similar to, yeah, then RT is always a field.
Uh,
The integral closure is a field. I don't know if that's what you were,
yeah, but see, C two is already a field.
yeah,
So that was my silly example. Any field is integrally closed because you're looking for elements of the quotient field of the field. Well, that's just, you're already there, right? So in a very silly way, any field is integrally closed. Here's a logic on this. This is a wonderful theorem. Let's be able to prove this. Really quick. Suppose R is a UFD with quotient field. And omega is A over B and K is integral over R. So suppose we find this integral element. I am also, by the way, anybody think of a convenient assumption that we can make here?
We gotta combine.
There we go. And we need UFD for that. Well, we don't quite need UFD, but UFD helps. Assume GCD of AB is 1. That is to say, if your fraction, if you have common primes in the top and bottom, cancel them out. Right? So omega is root of x to the n plus Rn minus 1, xn minus 1, R1x, that's R0. Well,
Then repeat our three with the 1/2, right?
that's right. So sweep the leg, Johnny. Sweep that B to the N out. Now, suppose, you know, is a non-zero prime. What's that? Five to be. So let's just suppose that I find a prime that divides B. Right? Notice that P divides A to the N. Right? Because P divides this, P divides that. Agreed? So P has to divide A, but P is a prime. Therefore, P is common divisor of A and B, which is a contradiction. Because A and B have no common divisor. Conclusion. No prime divides B. And what can we conclude about an element of UFD which no prime divides? It's 1.
So unit percent.
Well, close enough for rock and roll. So B must be a unit. Therefore, omega A over B is actually in R. And there you go. So every element that was integral actually was already in R because B, you're dividing by your name. Okay, any questions on that? Questions? All right, well, if there are any questions, remember to see me if you're having trouble getting caught up on your homework. Other than that, I will see you all on Wednesday.